Right. Good morning. Any questions or comments? So I want to start talking about integer quantum Hall effect, but in graphene. So all previous stuff we considered for quantum Hall effect were done in like so-called 2D electron gas, which is like a hybrid of like gallium arsenide, aluminum gallium arsenide heterostructure. But after like the discovery of graphene, I think in 2000s, like graphene was discovered. So which is like a truly two-dimensional material, 2D material. And of course it was reasonable to consider if quantum Hall effect could be realized in graphene. And that's what has been done, and I want to show you the theory and a little bit what comes out in the experiment. So to remind you, graphene has like this honeycomb lattice in the real space. So these are, if you want A sublattice, these are B sublattice. So this is real space. And in the reciprocal space, you also have like a honeycomb, but a little bit rotated. Something like that. So this is the Brillouin zone center. So this is reciprocal space, and this one is K point. This one is K prime point. And if you remember what we did some time ago now, these are like Dirac cones here and there, and there are like Dirac cone, 6 Dirac cones, like here, 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 and here. And the low energy physics was K prime was equal to, there was like some V Fermi scale, and this is plus or minus for K and K prime value, Px sigma x plus Py sigma y. So one for each, also like each valley comes with 2 spins and 2 valleys. In total we have 4-fold degeneracy, which will be important later when we like see the quantum Hall plateaus in this material. So what we'll do is we'll do what we did. So P will go to P minus E over C times A, which we define this to be. The valleys. So they're like this is like a Brillouin zone, right? Like you go to Brillouin zone, there are like 6 points in the Brillouin zone where valence band and conduction band touch, and so this is like conduction band. This is valence band, and they touch in its isolated singularity, which is like a Dirac point. So you can go look at those notes if you want, but it's like simple. We already did that.
But I can remember you call them valleys.
So the valleys, I see. Right. These are also called sometimes valley. So this is called valley degeneracy. Yes. Thank you. Reminding. Yes, that's correct. So this is plus. So now what I want to do is like first I want to reformulate quantum Hall problem in like a gauge independent form, like in terms of like this, which is like simple H is equal to P squared over 2m will go to pi squared over 2m. So this is like a vector, and this one is going to be pi x squared over 2m plus pi y squared over 2m. So I want to like convert this Hamiltonian to a harmonic oscillator without choosing a gauge. Previously we chose the Landau gauge and everything worked out fine. So to do that, what we need to remember is like these pi's are not like p, so they have different properties, and for this we can just look at the commutation. So this is px plus e over c ax, py plus e over c ay, and px and px are going to commute, and px and so ax is a function of x and y, and ay is a function of x and y. So px, which has like an x derivative, is going to act on ay, and it's going to go around. So if you do this, it's like a simple calculation. Let me just write the result: e h bar over c del x ay minus del y ax, and this is z component of magnetic field from the curl, and we took this to be minus b by convention. So if you want, magnetic field points in the minus z direction. That's why there is like an additional minus here, which is convenience sign. Then it happens to be I e h bar over c times b. Now I want to write this in terms of length scale. So if you remember, length scale was h bar over m omega, which was equal to h bar over m eb over m c, and this is h bar c over eb. Using this factor can be written as I h bar squared over L squared. And so this commutator, you can see something commuting with something else and giving I times a number. This should remind us commutation of x and p, and it was like I h bar, and we need to put this overall scaling to somehow here. And from here, if you remember, in the harmonic oscillator we define A something like m omega over 2 h bar x plus I over m omega p, and when we write the Hamiltonian in terms of a's and a deckers, we find h bar omega a decker a plus a half. So we want to do the same thing but with pi x and pi y. Let me do that. H is equal to 1 over 2m. Actually, let me just write the result. Let me just write you the definitions. So in this case, A is going to be defined like L over root 2 h bar pi x plus I pi y, and A decker is just let's pull this out. So this is A decker is just a minus here. From here you can calculate pi x, right? You can sum these two, and pi x is going to be h bar over root 2 L A plus A decker, and pi y is going to be minus I h bar over root 2 L A minus A decker. Then I can plug this in to h. H is equal to 1 over 2m. So I'll take these h bars out, h bar squared over 2l squared. So pi x is going to give me a squared plus a decker plus a decker a plus a decker squared. And similarly here there's like an overall minus, so this is going to be minus a squared plus a dagger plus a dagger a minus a dagger squared. So this is the bracket. So this a square is going to cancel this. This one is going to cancel this. And using the commutation, okay, maybe I can assign you this. I think it's like a simple thing, but let me assign this to you. Show a dagger. What should this be in the harmonic oscillator? -1 or 1? This is, I think in my notes, 1. Yes. Yes, I found it to be 1. At least for this problem, it is 1. And I think it's also 1 for the other usual harmonic oscillator. Maybe you can check your signs. And this means a dagger is going to be equal to 1 plus a dagger a, which is what should be. And that's what I will use here. This a dagger is going to be 1 plus a dagger a. This is 1 plus a dagger a. At the end, what this will amount to is like 1. It is 1, right? Yes. Yeah, 1 over. This is h bar squared over 4 m l squared. There is like 1, 2, 3, 4 a dagger a's. So this is 4 a dagger a plus 1, and there is another plus 1 plus 2. And this 4, I'm going to take it out and write it like this. So this is going to be 1/2. This is going to cancel. And this, if you look at this factor, h squared over m l squared is h bar over m omega. This is going to give you h bar omega. Then in this case we have h bar omega a dagger a plus 1/2. So same as Landau gauge, right? So this is for the usual quadratic Hamiltonian. Now I want to generalize this to graphene, and let's start with the k point. So h k is equal to V Fermi 0 px minus I py px plus I py 0. So this is our 2 by 2 and for you can also write, okay, let me actually write that. I only do hk because hk prime is exactly identical, so hk prime is going to be V Fermi 0 minus px minus I py minus px plus I py and 0. So we will do exactly the same thing. P will go to P plus, so P plus E over C A, and I'll shorten this with again pi, the vector. Then h k is going to be V Fermi 0 pi x minus I pi y, and this is pi x plus I pi y and 0. And now I go back and look at my definitions for pi x and pi y. So pi x plus I pi y is a, pi x minus I pi y is a dagger, and there's like an overall factor like this, and I can write this factor in front, so I'll write it like this. So this is V Fermi root 2 h bar over L. So root 2 h bar over L times, so this is 0. So this first diagonal is a dagger. So this one is a dagger, this one is A 0. Did I get that right? Yes, this seems to be correct. And this one, I want to define this E Dirac energy, and this is going to be E Dirac 0 A dagger A 0. Now, as a exercise in quantum mechanics, suppose I give you like this raising and lowering operators. I think you could even make this like a Griffiths level problem, right? Rather than A's and A daggers, I give you this form, and I ask you to diagonalize the Hamiltonian, find the eigenvalues and eigenvectors. What should we do? Any ideas? Suppose this is given. If it was like A dagger A, I automatically know N, right? But now it is not A dagger A. Also, it is in the matrix structure. What should we do?
You can solve eigenvalue equation.
But this is like an operator. How do I solve eigenvalue equation? What should I do? So if you have never seen this, this is a little bit disorienting, but this is simple stuff, right? This is just what you need to do is you just take square of this, ED squared. So let me write. You just write this times itself, and this is going to give you ED squared. So this is here A dagger A 0 0, and here it's going to be if I do this A dagger, and this A dagger I want to write it like A dagger A plus 1. And now it shows the structure, right? So this one I want to have like H psi is equal to E psi form, and now I can substitute like psi as here is N. If you want, you can try, right? You can try one, and if it doesn't work, you can try the other. Let me try N minus 1, and if you plug this in, so this H squared psi is going to give us ED squared. So N will act here, and it is going to be N, and this one is going to be N minus 1 plus 1 is N minus 1, and this is going to be ED squared N minus 1, right? This is an eigenvalue equation form. Then E N is going to be ED squared times N. Good?
Is it En or En squared?
Oh, En squared, yes. You're right. And so what I need to do is like I need to take the square root of this, and square root can be plus or minus root 2. And actually we like to write it like this absolute value here. I mean, and N is 1, 2, 3, dot.
Then there's the absolute value.
For the moment it doesn't matter, but in a little bit I'll rather than writing plus or minus, I'm going to put this indexing to here. I'll index from minus infinity to plus infinity, and I'll get rid of this. Actually, let's forget about that for the moment. You are right. But for Hamiltonians like this, we also need to be careful because there is generally a zero mode. How do I see zero mode? If you try HK, if you try to hit on something like zeroth, so these are harmonic oscillator levels, right? Usual harmonic oscillators, but we arrange them in like a column vector. Now I take the harmonic oscillator zeroth ground state, which is like a Gaussian if you want, and here I just want 0. That one column is trivial, the other column is like harmonic oscillator ground state. If I do this, it's going to be okay. Let's try it on HK. So this is going to be ED 0 A dagger A 0, and it's hitting on 0, 0, right? So this is a ket 0, this is like trivial 0. And if you do this, ED times, so A dagger times 0 is 0, and A, like lowering an operator hitting on A is also 0. That means it's like 0 times 0, 0. So this is like 0 mode. Sometimes I see people saying like, oh, 0, 0 is also 0 mode. 0, 0 is not a 0 mode. It's like 0, right? It's like trivial ket. So this one is non-trivial because there's like a non-zero element inside. And this non-zero, although you have non-zero element, eigenvalue is still 0. So then, okay. So there's these eigenvalues. So there's also E0, 0 eigenvalue. Then we can combine this in like a compact form. We can say En is equal to E Dirac sine of N root absolute value of N, and we can let N run from 0 plus or minus 1 plus or minus 2 and so on. Good. Now, once we see the lambda level, we should, in principle, be able to tell what we will see in the experiment. Right? Experiment is like a direct manifestation of lambda levels. But in this case, we have to be a little bit careful because of this zeroth level. Let me first remind you the experiment in the usual quadratic form, right? In the quadratic form, so we can either think about tuning the magnetic field for a fixed electron density, or we can like fix magnetic field and tune electron density. That means we are going to sequentially fill up the lambda levels. And here there is like some lambda level, here's another lambda level, here's another lambda level, and so on. So this one is, let me just try to align, something like that. And what we saw was inside the gaps, so these are gaps, these are bends, right? Because of disorder, these are going to be broadened. But inside the gaps, we have plateaus. So I have like a plateau here, I have a plateau here, and I have a plateau here. And as maybe another plateau, okay, it's going from 0, but it doesn't matter. And then we connect these plateaus. And this is sigma xy. And what happens is, like, as you cross lambda levels, the sigma xx, the usual conductivity, is going to just peak, right? And then in the gap, it is like insulator. Here it's going to peak. In the gap, it's an insulator. The gap, it's an insulator. Good. So this is the usual. So this is conventional. And in the graphene, it's going to be completely different. And let's try to see that. In the graphene, we have like a zero energy. So energy goes from minus to positive, minus values, negative values to positive values. And so I have, let me try to mark my lambda levels. I have one lambda level here. 0, I cannot show it, but like there is another lambda level here, another lambda level here. Let me just show 2, and I think that's enough. Another one here, another one here. So when you are on a lambda level, which is, okay, this is N, and this is sigma xx or sigma xy. So this one is sigma xx. So when you are on a lambda level, right? So for example, here is a lambda level. As I cross the lambda level, I need to have these like linear lines. I have like a linear line here, right? I have a linear, how do I draw this? I think it's a little bit nicer to do 2 steps, but it's okay. Let me start with sigma xx. When I am like on a given lambda level, I have these peaks. So this is sigma xx. The peaks are not going to be the same because I'll explain in a little bit. Density of states is going to change with energy, but for the moment we don't care about that detail. And when you are going through like a lambda level, you need to have like a linear form. So something like that. And in the lambda level, you are like flat, right? But you can see one lambda level step is going from like, okay, 1 square, 1 square. In the second lambda level, I need to go 2 more square here, right? From here to here. I need to make 2 steps. Like this. Another step. Here I have, okay, 2 steps. Like that. Good. Maybe a little bit more dramatic. So this is, if you want, so Dirac integer quantum Hall effect. And the difference here is because at charge neutrality, so this is the charge neutral point, and graphene is typically electron and hole symmetric. What this means is like if you don't do anything, total charge is 0, and you are here. And if you total charge 0 means there is like equal amount of electrons and holes. And equal amount of electron and hole means this lambda level is half filled. To fully occupy this lambda level, you need to just go half a step. Right? So this is half step. But now this lambda level is completely empty, and you start filling it from here. And to go from this lambda level to next step, you need to do full step. So this is full step. So, and also on this side, there is like a half, and there is full step. So it almost looks like a fractional quantum mechanics, but not. It is like trivial. It's just coming from like counting of electrons in the graphene. And the way we say this is like sigma xy should be E squared over h, and it has to have these integer steps, but 0th step starts with 1/2. And this n is again 0 plus or minus 1 plus or minus 2. So that's like for 1 degree of freedom. But we have 2 values. We have to multiply with 2 because the graphene flake in the experiment is going to know about 2 values. It cannot distinguish. And also spins. We have to have 2 times 2, 4. Okay. And this is generally absorbed inside. This is going to be 4n plus 2. So it is still integer quantum effect, but steps are a little bit different. Any questions? And this observation was, so I think I don't have the experiment today, but this was done by, does anybody know? So who invented graphene? So Novoselav, and Gaim in 2005. They not only isolated graphene flake, but they also did integer quantum Hall measurement, and they showed these steps, and it was the proof that like they actually isolated the graphene and they got the Nobel Prize. I don't remember how much, but like they got it very quick because it was like a big thing. So maybe I can assign you, like not to be too boring, a couple of exercises. If you are interested, you can do this, and then if not, that's also fine. let me call them homework, optional homework if you want. So one thing, the first one, compare Landau level spacing in usual quantum Hall effect versus Dirac. I mean, Dirac quantum Hall effect is graphene quantum Hall effect. And what I mean by this is, like, in the usual case, Landau level spacing is h bar omega, right? And this is h bar EB over MC. Whereas here, Landau level spacing, as you can see here, is going to be proportional to ED, and ED is going to be proportional to, where did we write it? H bar V Fermi over L. Okay. Here it is V Fermi root 2 H bar over L. Like, I don't know, choose B is equal to 10 Tesla, M electron. If you want, you can also put band mass, like take M electron times 0.1 if you want, right? That's the reasonable thing. And E is fundamental constant, C is fundamental, H bar is constant, and find Landau level spacing. And here you can see there's no mass scale, but there's like a V Fermi. And V Fermi in graphene, we mentioned that a little bit. I don't know if you remember, but it is like something like 10 to the 6 meter per second. It is like 300 times smaller than speed of light. And L inside there is like a magnetic length we defined above, and compare this level spacing. And what you are going to find is, okay, maybe I can give you, if you convert this is corresponding to something like 30 Kelvin. 30, I found 30, 40 Kelvin. And this one, the second one, is about 2000 Kelvin. And what does this mean? So if Landau level spacing is much bigger like this, even in not terribly large magnetic fields, that means you can observe this effect even in room temperature, right? Even like you don't need to go to cryogenic temperatures. And real temperatures, there are like some corrections to this. It's not 2000, but room temperature is low enough to see this effect. Of course, you need to also have like a little bit better sample quality and good mobility, and you need to have like some other requirements. But at this is giving you like a head start. So the second thing to consider here is find spectrum using Landau gauge. If you want to see if you understand how to use Landau gauge, you can do this exercise. And Landau gauge was something like this: 0 minus bx 0. And you also going to do the same trick. You are going to square the Hamiltonian, and you are going to compare it with the usual case, and then you are going to find the same spectrum. But this exercise is going to teach you the degeneracy of Landau levels are the same. So it's like n phi, which is B times A divided by flux quantum. So show this to convince yourself. And okay, there's one last, and I think this is, I would want to do this in the lecture, but I think there's not enough time. So find the density of states in graphene. Have you ever done an exercise like this in 409?
Probably.
No, right? Huh?
Probably.
Like, so graphene is like, okay, this Dirac cone, right? It is like, and energy is some V Fermi times P, right? It is like a linear dispersion. And you are going to do exactly the same thing we did for quadratic dispersion. So here is energy. Here is, if you want, so this is density of states at energy. So this is energy, and it's since spectrum is linear in P and E are proportional. You can also see it's going to be something like that. Compare this, like in the usual quadratic case, we only have positive energies and it was flat. And now imagine putting these electrons in the lambda level, right? You can see there's like less states here, right? Less states here, and to fill the lambda level, which has the same number of states, you need to have like a bigger gap here, right? Because the area is decreasing here, you need a bigger area here, and like something like that. But here there is like height is a little bit higher, so you don't need as much area. And here even more so, like here, right? And these are all going to be like lambda levels, and that's why the spectrum, like the lambda levels in the graphene, is like unequally spaced, right? It goes like that's the reason it goes like ED sine of n root n, whereas in the usual case it goes like h bar omega n plus a half. It goes linearly here, it doesn't go linearly here. And you can also like do exactly the same thing. Like, so what should be the, like, if you remember what we did was like, we started with the usual density of states, and we said it should collapse to these lambda levels, and we automatically find the new density of states. Here you need to think a little bit more, like how can you just collapse all of these like areas on a given lambda level, and it's going to give you the lambda level structure of the graphene. Lastly, and we'll I think do this, and I'll finish after this. Third one is, so if you remember, we started with like a tight binding model in graphene, like Tij, Ai dagger Aj. And when there is like a magnetic field, there is like so-called Paris substitution. Maybe else substitution. And what this means is like, okay, this is like some tight binding model, Ij. And from here we found the Dirac cones. In the Paris substitution, what we need to do is like Tij should go to Tij times, does anybody remember? There's like some vector potential, minus I, h bar over E over h bar c, Ri to Rj, dr dot A. And this is going to give us like a tight binding model independent of like Dirac cones, and we'll also do that at some point. And this is going to give us Hofstadter butterfly. But the calculation we did in this course is like much more economical, and it is like directly like helpful to see the experiment. Okay, any questions or comments? Okay, I'll stop here. Thank you.